Good morning, everyone. Welcome to this session. Today, I'm going to talk a little bit about our solving urban problems with the Cesium and the simulation-based digital twin platform, so-called TwinSpace. I'm the primary presenter, Kyu-Sung Choi, and I also have my co-presenter, Mr. Sang-Kyun Kim. Would you please? One of the developers of the TwinSpace platform. However, to save our time, I'm going to lead most of my presentation. Please understand that. Let me briefly introduce who we are. We are the developers of the TwinSpace platform in SHINHAN aerial survey. SHINHAN is a Cesium certified developer organization located in South Korea. We are traditionally specialized in surveying and mapping and quality data services and so on. But we recently faced some challenges like requests for ready-to-use solutions. Oh, next. I'm sorry. Oops. Oh. Which one? This one. I'm sorry. I'm confused. We were recently faced some challenges like requests for ready-to-use solutions, and we responded the challenges with a digital twin platform based on Cesium technology, which has a brand name, TwinSpace. So more about the company info, you can refer to this web link. The challenges that I mentioned previously came from the voice of our customers. They are, what's next after data acquisition? How to make the best of valued data? Request for help to solve real-world problems. And most of the customers are our local governments. So, excuse me, and an approach. Confronting with such a situation, we had an approach of listening more to our existing customers' voice and leveraging data acquisition and construction capabilities of our own and launching a problem-solving solution services. And an approach to build once and deploy multiple times guided us to a platform strategy. To solve our customers' problems, we recognized a couple of requirements. First, in order to support quality decision-making, enabling simulation were needed. And to improve situational awareness, providing visualization in virtual space was needed. These needs were regarded solution requirements and became an inception of digital twin solutions strategy. This concept is well drawn at the lower right side of this slide. Based on the voice of our customers, two major problems have caught our attention. The first one, in management of underground utilities, there were being lack of intuitive visualization. And the second, in preparedness against extreme rainfall, where a lack of predicting submerged areas are. To address these issues, we concluded that simulation-based analysis as well as 3D virtual space was required. Here, 3D virtual space plays a role of problem-solving playground and This strongly motivated us to adopt Cesium. These conditions drove us to develop solution applications designed to work in 3D virtual space. Now, let's see how we have a solution for underground utility problem. Having visual simulation capability, the goal was to visualize target underground utilities like water pipelines and sewer pipes from 2D data to 3D model. And to improve situational awareness of identifying overpasses, underpasses, and relative sizes of the utility lines. Regarding the input 2D data, water pipelines and sewer pipes are accompanied by separate point layers, which check the line depth from the surface. Thanks to the depth values of the lines measured down from the surface terrain, the lines can have absolute altitudes above the mean sea level. At the same time, by using the diameters of utility lines, the lines could be converted to 3D cylinders, like this picture, for the water lines and the sewer pipes. This conceptual visualization process was achieved by two distinct data conversion options. Option A is an on-the-fly visualization that dynamically converts input data upon loading. The other option, this is the option A, the other option is a persistent visualization that processes input data to create 3D tiles. Eventually, both results are visualized in a Cesium environment. From the Cesium-focused standpoint, in option A of on-the-fly visualization, Cesium.js is used to convert input shapefile data to a CZML format, while in option B of the persistent visualization, Cesium is used to create 3D tiles where the input data is already pre-processed to KML COLLADA format by our own command line interface utility tool. I'm not talking more about the command line utility itself. Please understand that. And both results are visualized in Cesium.js environment like this. Here are some of the screenshots of the visualization results. Having this kind of visually interactive operations, customers are very happy to have a better situational awareness through browsing underground utilities at their own will. Now, here is a demo video that captures actual operations and with our platform. This consists of two parts, one for on-the-fly visualization, the other for persistent visualization, as I told you before. So for your better understanding, please see the caption at the lower side of the screen. So let's see. The two-dimensional data is visualized on QGIS. This is actually the shapefile, and it is loaded through the user interface, and upon loading, the data is converted to 3D data, and we can visualize. This is the water pipeline, and we also can identify the 3D features and its attributes, and this is the manhole. And this is a bulb. And now for the sewer pipes, we have the same process like water lines. It has a different structure from the water lines. And the purple color means the sewer pipes. And we also identify the attributes and a manhole as well. Now, let's see the combined water lines and sewer pipes all together at the same screen. Now, let's see the persistent visualization. We have a command line interface utility that converts shapefiles to KML COLLADA. And once they are converted like this, then we upload them to Cesium. Actually, this is a Cesium self-hosted, the on-premises solution. And then it converts to 3D tiles. And now let's see how it looks. Apparently, they look very similar to the CZML file that we had on the fly visualization. You may see the water pipelines are not tightly connected, but there is some measuring error that reflects that. And we also have valve. Okay, that is one application. And the other one. Next, we'll see the way how we made a solution for extreme rainfall problem. Here, applying computational simulation, the goal was to predict submerged areas and to support time series animation over time, depending on what-if scenarios. Having input geospatial data and simulation parameters, a flood simulation program runs to create submerged area outputs over time. The animated visualization is also achieved in a Cesium.js environment. In this solution, however, Cesium has limited use and only for visualization purpose. The flood modeling or flood simulation is achieved by open source tools, GrassGIS, and its extension called ITSE. This modeling tool is very flexible to apply and customize simulation parameters in Python environment. When flood depth maps are created showing submerged areas, they can be visualized in time series animation with the Cesium.js embedded open source called Terra.js environment. Though Cesium.js has a limited use, it still contributes to provide valued 3D virtual space. Here are the screenshots of the simulation results over time. The input parameter was 2-hour contributing rainfall with a rate of 100 millimeters per hour. The first four, 1, 2, 3, 4, images show the flooding during the first 2 hours. And the last 2 images show the flood recession during another 2 hours after the rainfall stop. The animation over time can be made for the visualization. Here again is a demo video that captures actual operation. Let's see. Here we go. we enter input parameters, but it depends on the condition. And running simulation at the back end behind the scene, and we saw the results, and they are populated at the table of contents, and the time series data are played as an animation. So it starts from raining during the first 2 hours, flooding continues. And now rain stops and the flood recession starts. So the submerged areas are disappearing. And we can visualize the submerged areas as we navigate through the neighbors. So this is the result of our flood simulation app. The two solution apps run on our TwinSpace platform. Its technical architecture is shown in the picture. One of the characteristics of the platform is that it's packaged with a Cesium licensed product, so-called Cesium Ion self-hosted, and open source technology. And SHINHAN provides the solution platform as a licensed product as well as professional service. To summarize, let's think about what the lessons we learned from this practice. 1. Cesium Ion self-hosted at the back end lowered our burden in dealing with 3D virtual space. 2. Cesium.js and Terra.js, the ready-to-use web library and app at the front end, also helped us to focus more on solutions domain expertise. Without them, we must have spent a lot of time. 3. From problem-solving perspective, 3D geospatial approach really makes compelling perceptions, and interactive visualization improves situational awareness. So I would say that 3D geospatial content plays a role of a visual language. This is my final slide. And then what's next with the TwinSpace platform? It's only in the beginning stage, so more of the functional improvements and improvements are needed in the near future. For the underground utility app, visualizing after surface excavation and augmented reality support are planned. And for the flood simulation app, drainage flow support with the SWMM, the famous SWMM model, and bidirectional coupling between drainage and surface are also planned. Besides the two apps, we need more apps reflecting customer requests. They are considered. So finally, we need to align with the 3D Tiles 1.1 advancement by making the best of GLTF content and leveraging rich metadata. Is there anyone who has listened to what's new in 3D Tiles? I'm very interested in that. And these are our future plans to do ahead of us. This is the end, and thank you for kind listening.